To further extract the contents of the response x to a sinusoidal complex input e to the j omega t, we need to extract the real part of all this and the complex part of all this. By now, you probably know how to do that. We first do a fraction expansion by writing that 1 over ms squared plus mu s plus k times 1 over s minus j omega, it equal to a plus bs divided by ms squared plus mu s plus k plus c over s minus j omega. Reducing to the same denominator, we look for the values of a and b and c by writing that this must be equal to that and therefore equal to, with the denominator being the same, and the numerator being equal to a plus bs times s minus j omega, and then plus c times ms squared plus mu s plus k. So if we look at the terms in s squared, we obtain bs squared plus cms squared, and there is no such term on top, therefore b plus cm must be equal to 0. Now if we look at the terms in S, we get that a minus bj omega plus c mu must be also equal to 0. And the reason is because there is no term in S there. Finally, looking at the constant terms, we have minus a j omega plus ck that must be equal to 1. Now, when we do this partial fraction expansion, we see that it is easy to replace a by its value as a function of c, b by its value as a function of c, and then plug them in the middle equation. We have b is equal to minus cm, a is equal to ck minus 1 divided by j omega, and therefore the middle equation gives us ck minus 1 divided by j omega minus or plus Cm j omega plus C mu is equal to 0. This gives us an equation in C that we can now solve by writing that C times k over j omega plus m j omega plus mu is equal to 1 over j omega, or C times k minus m omega squared plus mu j omega is equal to 1. Or C is equal to 1 over minus m omega squared plus mu j omega plus k. Now this is fairly important, and let me explain you why. Without even going to the computation of A and B, we therefore have that x hat is equal to A plus BS divided by ms squared plus mu s plus k plus C over S minus j omega. And where C is this term times 1 over minus m omega squared plus mu j omega plus k. Okay? So let's look at the long-term behavior of x. This term can be quickly studied by using the initial value theorem. The limit of this term written in the time domain that I will write as y of t when t tends towards infinity is equal to a plus bs, etc., etc. The limit when s tends towards 0 of s times y of s, which is equal to s times a plus bs divided by ms squared plus mu s plus k. Therefore, this term tends towards 0. That term is named transient. Now this term is just 1 over s minus j omega times this thing. And I want to single it out to see what it means. So let me move this page away and then restart with a new page. What is this term? 1 over minus m omega squared plus mu j omega plus k times 1 over s minus j omega. Well, it is a constant factor times a sinusoid, meaning that if we take the inverse Laplace transform of this guy, we obtain 1 over minus m omega squared plus mu j omega plus k times e to the j omega t. That is that part of x of t that we have kept and that has not died off. So it is x of t when t tends towards infinity. Now what can I say here? First, this is the same term as what we had as an input. And so the long-term behavior of x is that of a number times the input. A complex number, but a number. Second, this is all as if, having defined h of s as the transfer function that of the system, that is one over ms squared plus mu s plus k, this guy is h of j omega. We therefore find that x of t is equal to h of j omega times e to the j omega t. That is a very important result. And I'm going to detail you how and why now. From this, we also have the long-term response of the system to sinusoidal and cosinusoidal inputs. Why? Well, as I said, the response to the cosinusoidal input is simply the real part of the response here. If the input is e to the j omega t is equal to cosine omega t plus j times the sine of omega t, I can write that the long-term response of x of t, so when t tends towards infinity, of x of t, which is equal to h of j omega times e to the j omega t, will be such that the real part of this guy goes to the response to a cosine, and the imaginary part goes to a response of a sine. In this particular case, what we simply can write is that h of j omega e to the j omega t is equal to h of j omega times cosine omega t plus j times sine omega t, and therefore is equal to h of j omega cosine omega t plus j times h of j omega sine omega t. Now, the real part will be, if I extract the real part first, it will be a real part of h of j omega times cosine omega t minus the imaginary part of h of j omega sine omega t plus j times the imaginary part of h of j omega times the cosine of omega t plus j times the real part of h of j omega times the sine of omega t. Therefore, if now the input f is cosine omega t alone, the long-term response of the system, that is the case when t tends towards infinity, will be this guy. The response of the system to sine omega t will be this guy. And you can go ahead and compute the real and imaginary part of h by using its expression, which is here. Okay, so that being said, you will probably agree with me that it is much easier to consider the response to a complex input e to the j omega t rather than the response to a real cosine omega t or the response to another real sine omega t. Which is why people often consider this to be the way to work with the sinusoidal response to the system.